Hi everyone and welcome. So the last two sections of chapter 5, we're going to be getting a little bit into the weird, but in a good way. It's interesting stuff that I think it's worthwhile for you to have seen at this point in your mathematical careers, and that comes up surprisingly often as you get into more advanced mathematics, especially when you're dealing with analysis. So here's where it starts. We're looking at Laplace transforms, and every once in a while, you are working on a Laplace transform problem, and you're in the Laplace domain, and you come across something that looks like this. It's a product of two things that when you look at them individually, you know what their inverse Laplace transforms are. You've seen that kind of thing before. But here they are being multiplied by each other. Now, we have some techniques for undoing that so far. That's basically what the method of partial fractions is, and that works in a lot of cases. So that's a way for us to take things that are multiplied together like this and separate them. And that works. But sometimes you'd like to, or you can't do that because it's not an appropriate method, maybe it's not a rational function. But anyway, you want to know how to undo this. Right? If you have a function f and g, and you know that the Laplace transform of each one, and then you come across the product. How do you find the inverse Laplace transform of that product? And, of course, it's not as simple as the product of f and g. It's just not. It's almost never, I'm going to go with almost never, maybe it's actually never, actually equal to the product of f and g. So it turns out that the thing that it is this thing called the convolution of f and g, which is denoted by f star g. So you say f convolved with g, or the convolution of f with g, or we just say f star g. So what's this thing? What on earth is the convolution? Well, here we go. So by definition, so this is the definition of convolutions for functions that are only defined for t greater than or equal to 0, which is what we're dealing with in Laplace transforms. So if we have a function f and g defined for t greater than or equal to 0, then we define the convolution of f and g to be the integral from 0 to t of f of t minus lambda, g of lambda, d lambda. So lambda here is a dummy variable that we're just using to fill in. And so the thing that comes out of here is going to be t. So notice that it's the same t here and here. When it's not in the context with t greater than or equal to 0, actually this integral looks exactly the same, except we replace the bounds with minus infinity and infinity. And in some context, convolution, in a lot of contexts, the convolution integral is defined in that way. It's surprising how often convolution integrals actually come up, even though you might think you've never seen one before. In fact, it turns out that you have. So let's start by just doing a calculation of one. Let's see what that looks like. So suppose that I want to find t star sine t. And so by definition then, let's write this down, t star sine t. That is going to be equal to the integral from 0 to t of, well, we need to take our first function and plug in t minus lambda, so t minus lambda, and then sine lambda d lambda. All right, so this is a pretty straightforward integration problem. We're going to break it up first by distributing. We're going to have the integral from 0 to t of t sine lambda d lambda minus the integral from 0 to t of lambda sine lambda d lambda. All right, in this first integral, we can pull out the t, because this is an integral with respect to lambda, that's a constant, and we just have sine lambda d lambda on the inside. For the second one, we're going to go ahead and do integration by parts, so we need a u and a dv. The obvious choice is for u to be lambda, and that means dv has to be sine lambda d lambda. So we get du is d lambda, and v is minus cosine of lambda. Okay, so putting this together then, we get minus, what will it be? uv, so negative lambda cosine lambda, evaluated between 0 and t, minus the integral from 0 to t of v du, so minus cosine lambda d lambda. Lots of minus signs in there mess us up a little bit, but we'll be all right. All right, so first one, t, here we have minus cosine lambda between 0 and t, minus let's see, we're going to get minus t cosine t plus 0. And then over here we have plus, our antiderivative is sine lambda, going from 0 to t. Okay, have I got my signs right there? Oh, sorry, no, it's a minus sign here. Right, because we have 1, 2, 3 minus signs. So we get a minus sign right in there. All right, so now plugging into our first term, we have t times negative cosine t plus 1 plus t cosine t, and then minus sine t minus 0. All right, so our t cosine t's are going to cancel, this guy and this guy. And what does that leave us with? That leaves us with, that's going to leave us with a t and a minus sine t. There we have it. So it turns out that the convolution of t with sine t is t minus sine t. I guarantee you that is not how it always works out. So you have to work through these things a little bit. Try them on your own. For example, if you just want to do a quick one on your own, try t star cosine t and see how that one turns out. It works out a little bit differently, but similar kind of a deal. Basically, if you're just looking at things, it is quite hard to tell what the convolution of two functions will be. It's hard to develop intuition about them. So just try some, see how it goes. Another challenging one that you could give a shot is if to work out what would happen with some step functions or boxcar functions, functions that are step up to a certain height and then come back down to 0. So for example, if f were equal to 1 from 0 to 1 and then 0 afterwards, and then g were equal to 0, then jumped up to 2 from 2 to 4 and then back down to 0. These are called boxcar functions because they look like this. So one of them would be, f would be a graph like this. Well, it doesn't really have a vertical part, but it would be something like this. 2, 3, 4. So it's 0, and then it jumps up, and then it's 0, and then it comes back down, and g would be 0 until 2, then it jumps up, and then it goes back down over there. So because they make little boxes like this, these are sometimes called boxcar functions. So what happens if you convolve those two things against each other? That I've worked out. That's in a separate video that you can take a look at in the playlist. We're not going to do that here because that would just make this video way too long. So moving on. We can get some algebraic properties of convolution integrals. I've just listed a few of them here. There are also some nice properties that involve derivatives and things like that. But here are the main ones that we're going to need to know. So the first is commutativity, right? Remember that f and g have different roles in that integral, but it turns out that with a change of variables, f star g and g star f are equal to each other. So that's nice. We also have linearity. So basically f star, a linear combination of two functions will just be the same linear combinations you would expect. So c1 f star plus c2 f star g plus c2 f star h. So it's basically the distributive rule works the way you think it would. And it's also associative. So f star g star h is the same as f star g star h. So if you do first f star g and then star that with h, or if you do first g star h and then star that on the left with f. So it turns out that you've actually seen these kinds of things before, though you might not have recognized it. If you go back and look at the formula you get when doing integrating, multiplying by an integrating factor, and you work it all the way through from a constant coefficient, it turns out that you get something like this. All right? And this is exactly a convolution integral. This last one here is this whole bit here is e to the alpha t star g of t. So you've seen them before, though you haven't had maybe the tools to recognize them as convolution integrals. They come up. They also, a convolution shows up in the formula for the variation of parameters formula under certain circumstances, if you start with something with an initial condition equal to the identity for your fundamental matrix. All right, so we've got some good algebraic properties, but let's get back to the reason that we're actually doing these things in the first place. That is what's called the convolution theorem. The convolution theorem tells us the thing that we started with, that the Laplace transform of the convolution of f and g is the product of the Laplace transforms of f and g. So what do we have to do to prove this thing? So let f and g be piecewise continuous and exponentially bounded. So that means that they have Laplace transforms, right, on the interval 0 to infinity, and let f of s and g of s be their respective Laplace transforms. Then it turns out that f star g also has a Laplace transform, meaning it is also piecewise continuous and exponentially bounded. And furthermore, the Laplace transform of g of t is equal to f of s times g of s. All right, so what do we have to prove? So first we need to prove that f star g even has a Laplace transform. So we need to prove that f star g is piecewise continuous. Now I'm going to go pretty quickly about these first things and not include all the details. They're covered pretty well in the book. So is it true that f star g is piecewise continuous? In fact, it turns out that f star g is continuous, even if f and g are not. So it's also piecewise continuous, right? Continuous is a stronger condition than piecewise continuous. And if we look at whether f star g is exponentially bounded, which is also required, it turns out that yes. I don't want to go through the details of that right now. So have a look in the book. That's covered pretty nicely. So we shouldn't have too much of a trouble with that. What I want to focus on instead is the calculation of the actual Laplace transform. So I want to find the Laplace transform of f star g. Right, so by definition, this would be the integral from 0 to infinity of f star g of t times e to the minus st dt. Right, that's textbook definition of what the Laplace transform of a function is. And now we're going to put in the definition of f star g, so we're going to have an integral inside of an integral. This is from 0 to t of f of t minus lambda, g of lambda, d lambda, right? So that's being multiplied by e to the minus st dt. Okay, so we're going to turn this into a double integral first. So bringing all the terms together, 0 to infinity, 0 to t, f of t minus lambda, g of lambda, e to the minus st, d lambda, dt. Now it helps, we're going to do a change of variables to try and pull these things apart from each other, which we can't really do right now. We can't get the t's and the lambdas separate from each other, unfortunately. But let's look at what the region is that we are graphing over. We have two different variables, lambda and t. And this says the inner integral is with respect to lambda. It says lambda is always going to be going from 0 to t. Okay, so we need the line lambda equals t, which is exactly here in this plane. And we're integrating from 0 to t, so things that look like from 0 to t, right? Lambda goes from 0 to t. And then t goes from 0 to infinity, so we get all of these. So in the end, this is the region that we are integrating over. This is the region of integration. Well, we're going to reimagine this. We're going to rewrite the same thing, but instead we're going to go like this. Right, so how would that work? Well, that's reversing the order of integration. So we're going to be doing this now. Instead of d lambda dt, it's going to be dt and d lambda. And we have to figure out our bounds. So t now is always going to go from lambda on the low side to infinity on the top side. And lambda hits all of the values between 0 and infinity. Right, so we don't need to change any of the variables for this. This is still f of t minus lambda, g of lambda, e to the minus st, dt d lambda. Right, so let me move that a little bit closer. dt d lambda. All right, so now only one last trick to do. The next thing we want to do is we want to move this down to 0 so it matches the formula for Laplace transforms. So we're going to substitute. U is going to be equal to t minus lambda. This is in the dt integral, so du is just equal to dt. And of course, if u equals t minus lambda, then t is equal to u plus lambda. All right, let's see how that goes. So the outside integral is unaffected, 0 to infinity. And now, what are the bounds of integration? Before, this was from t equals lambda to t equals infinity. So for u, that's going to be from u equals, when t equals lambda, u equals 0. And when t equals infinity, u is also infinity. F of t minus lambda, that's u, g of lambda, e to the minus s. Now t is equal to u plus lambda, dt d lambda. All right, we're going to break up our exponential. This is equal to minus su, e to the minus su, e to the minus s lambda. And now we can pull the integrals apart. So we get the integral from 0 to infinity. We can get everything with the u and move it in front. Oh, I've made a slight mistake. It's not dt anymore. After we've made the change of variables, it's du. And everything's been changed over to u. So let's get all the u's together. We have f of u. F of u, e to the minus su, du. And then we have the integral from 0 to infinity of g of lambda, e to the minus s lambda, d lambda. And if we look at the definitions, what do we have here? That's the definition of the Laplace transform of f. That's the definition of the Laplace transform of g. So we get f of s, g of s, which is what we needed to prove. So the Laplace transform of f star g is f of s times g of s. And if we translate that back in terms of the inverse Laplace transform, so let's see, f star g is equal to f of s, g of s, and that also means that the inverse Laplace transform of f of s, g of s is equal to f star g, right, which is the thing that we were hoping to prove. All right, so that's it for now. I have, again, we're going to work out some examples of things like this. So have a look about that. Right, as I mentioned, we have this boxcar problem that we're going to work out in a separate video. And then we're going to be moving on to talk about the Dirac function and how that interacts with all of this fun